Okay, I think we're online now. Okay, so these days what we do is we'll run pip install Spark, and that usually works, which is nice. Sadly, this doesn't work on DataHub because DataHub doesn't have the necessary things, but if you run it on your own laptop, you can probably recreate this demo with some installation. And so if I run this code here, it's going to set up a Spark cluster on my own computer, and my computer has 4 cores, which means that I can run 4 things in parallel at the same time, roughly speaking. You can imagine that I might not only have my computer, but I might have like other computers at home that I have access to. And if I set up Spark on all those computers, I can use all those CPUs on those computers as well. So if I have a desktop at home with 16 cores, Spark can take the 4 cores on my computer and join forces with the 16 cores on my home desktop computer and run some code, which is really nice. Okay, so I'm gonna run this. It's gonna take a little bit of time to spin up the Spark session. And what I wanna show you is the types of speedups we can get by running code in parallel, okay? All right, I have to work fast. I'm having too much fun with these animations. Okay, so I have here some data, and this data come in this distribution. I simulated this data by just taking some random numbers and squaring them and then subtracting some other random numbers. Because this is just some data let's suppose that this is a data set that we have access to. And we want to compute the bootstrap mean for this data set. So I'm going to resample the data. And I see here that I get a mean here of about -7. If I run this, I'm going to stay at -7 because the random seed here tells Python to perform the random computation, but the random seed says do the computation in a deterministic way, which means that if I change the seed, the number here will change, like so. But if I don't change the seed, then it'll rerun the random code every time. Okay, so usually what we'll do when I have random code is I'll set the seed beforehand so that when I give the notebook to you, you'll get the exact same numbers as me. Okay, so if I gave you this code and you ran it yourself, you would also get -6.94 because we both had the same random seed. So it's a way of kind of like setting up the randomness in Python in a certain way so that other people can recreate your code. Like so. Okay, so let's change it back to 42. What I'm going to do here is take 10,000 seeds, and I'm going to bootstrap my data 10,000 times and compute the means for each one. And here is the bootstrap distribution of my sample means. Okay, and the IPython magic timeIt command will run my code multiple times and try to figure out on average how long my code took to run. So if I run that code and let it just chug along, what's happening behind the scenes is that it's taking this one line here, running it like 7 times, and finding out how long it took to run each time to get an average runtime for a piece of code. Fairly useful when you want to know on average how long a piece of code will take. So in this case, I see that this code here took about 3 seconds to run, plus minus 44 milliseconds. Okay, so what I'm going to do here is do the same thing, but in Spark. In Spark, I ask Spark to parallelize the seeds, which means that it'll store the seeds in a resilient distributed data frame. And then I can ask Spark to map a function across all the seeds that I have. I'm going to do that. And if I run samples.count, we see here that it takes a bunch of time. If I run samples.collect, I'll get the same distribution as I did above. So I'm running this in Spark. Now, what I can do here is ask for the mean of my bootstrap sample means, and I'll run the same computation, but now running it in parallel because we're using Spark. So if all goes well, I should notice a decrease in time. And I should notice a decrease in time of about a factor of 4, roughly speaking, because I have 4 cores. So in theory, we're running code across 4 cores at the same time. But we don't actually notice a 4 times speed up because when it comes to distributed computing, there's always some overhead associated with the cores talking to each other. In other words, if I gave 4 people here in this class an essay to write, it wouldn't take them 1/4 of the time to take one person to write an essay. It will probably take a little bit more than 1/4 because the people in the group need to like talk to each other to figure out who's writing what, roughly speaking. Okay. In Spark, we can cache computation. So if I ask it to persist my data transformations, the first time I run it, it will compute all the bootstrap samples and take the mean. But the second time I run it, it runs much faster because now it's remembering the data from before. So I can ask Spark to cache some results from before. Okay. Now in reality, Spark, what you'll often see with Spark is that you'll use the dataframe interface to it. So in Pandas, we have this NBA data set that I showed you from before. And if I ask Spark to create a data frame from this Pandas data frame, I can do a lot of Pandas-like operations, like this one up here, but it'll run them in parallel. So I can work with large-scale data, like so. And I can also use SQL. Spark has a SQL interface. So in practice, it's useful to know kind of like the basic Spark mapping and reducing operations. But in real life, oftentimes what you'll do is you'll take your data set, toss it into Spark, and then use the Pandas interface to Spark or the Spark SQL interface in order to actually do operations on this data. And it's a convenient way of just working with gigabytes of data on your own laptop. Or if you have access to a lot more machines, you can work with larger and larger data sets. Okay. Yeah, question.
So if you are in Spark, you can choose Pandas call, does it still run in parallel, or does it really just convert to Pandas like?
Yeah, so the question was, if I call this to Pandas, will it still run in parallel? The answer is it will run the SQL in parallel. And so even if my data are too big to fit on one machine, if the SQL result I can store on one machine, it will run the SQL in parallel, but this to Pandas call will probably, I believe this is a Pandas data frame here. So this is like, it's doing some computation involving all my cores, but then here I'm converting to a regular Pandas data frame that doesn't run anything in parallel. But I could opt to keep it as a Spark data frame to do more parallel operations on it. Okay. I also asked some questions yesterday about what is expected to know from the Ray lecture. I will not expect you to know like the intricate APIs of Ray. I don't need you to know what an actor is in Ray or a task is in Ray, although it's useful to know those things. But what I do want you to take away is the parallelism part of the lecture. So you should know, okay, if I run this in parallel, how much speed up can I expect to see? What are some ways of improving that parallel time run? So we saw like the add operation. And if you like work out that parallelism in a specific way, you can speed up the adding operation but it takes some thought to like get the parallelism just right. So you will have to know like, okay, if I run this code in serial versus running it in parallel, how much faster will it run? But you will not have to know like what a parameter server is or the APIs of Ray. Okay. All right, that's part 1 of my lecture. We're going to part 2, which is on decision trees. But let's take a break and fill out attendance. All right, and we'll come back in 2 minutes. Keep it short. All right, let's bring it back. I hate to cut your break short, but we started a little late today, so I'm like trying to keep things rolling. Okay, so as a reminder, project 2 due today. Make sure it's in. Project 3 is out today and will be due Tuesday, and our final is happening next Thursday. 10 Evans may change, so we're in the process of booking the room, but hopefully our final will be in here in 10 Evans. For the final, you can bring 2 double-sided handwritten cheat sheets, so which means you can bring the one you wrote for your midterm and make a new one for the material after the midterm. Bring a pencil and eraser. So I had people bring a pen last time, and they had a pretty bad time because they were trying to bubble in things, but they made a mistake, they crisscrossed it out, and then who knows what happened to their auto grading? Who knows what happened to the machine when the machine tried to read in those things? I think everything worked out okay, but if you don't want to go through the hassle of doing a regrade request for every single thing that you marked wrong, bring a pencil and eraser. And like the midterm, we'll provide for you the reference sheet. The reference sheet for the final is the same as the reference sheet for the midterm, just so you know. Okay. I want to talk to you about decision trees. And decision trees are a fun machine learning algorithm that also has some interesting ties to some material that we learned earlier on in this course. So what I'll do today and tomorrow is introduce decision trees, introduce an augmentation decision trees called random forests, and that'll kind of round out the machine learning part of this class. Okay, so in a decision tree, what we do is we fit a set of binary rules rather than a set of coefficients for a linear model. So for example, if I fit a decision tree, the decision tree might be something like, I might ask the question, okay, should I drive to San Francisco today or take the BART if I want to save the most time? And the way I can do that is I can make a set of binary rules. So I can say, okay, if it's the weekend, then I'll drive because there's less traffic. But if it's earlier than 10 a.m., I'll take the BART because the Bay Bridge is destruction before 10 a.m. and probably after 10 a.m. too, to be honest. But I'll also say, okay, if I can use a carpool lane, then I'll drive because if I have a friend, the carpool lane is pretty free usually, so on and so forth. So I can just make a sequence of rules to decide whether or not I can drive to San Francisco or take the BART. And decision trees give us an algorithm for automatically creating these rules from data. Okay, so I might start in this decision tree by asking about the day of the week. I'll call this my first feature, x1. Let's say on Sunday, I'll drive. On Saturday, I'll drive. But if it's a weekday, then I want to ask about the time of day. Okay. If it's before 10 a.m., then I'll want to know if I can carpool. But otherwise, I'll say, okay, if it's between 10 and 4, maybe I can drive because it's not as much traffic. But after 4 p.m., I also want to BART because people are trying to get back home from work. So on and so forth. Okay, so this is kind of the goal of the decision tree classifier. But you can also use this for regression by saying, okay, if it's Sunday, then just predict 10. And if it's Saturday, predict 20, for example. Okay. So another way of looking at a decision tree is that it cuts up our feature space into rectangular segments. What do I mean by that? Let's say that I have x1 on the x-axis and x2 on the y-axis here of this box. If I ask for a day of the week, I might say, okay, on Sunday, Monday through Friday, and Saturday, I'm going to do different things. So on Sunday and Saturday, I'll drive. But Monday through Friday, I need to check x2. And I'll divide up this space here, this rectangle here, by asking about what are the times I want to look at. And so I can say, okay, in this chunk here, I'll drive. But if I end up in this block here, I'll take the BART. And if I end up in this block up here, I need to check more features. Okay, so you can kind of see here that if I have a lot of these rectangular segments, I can model a lot of complicated decision boundaries. So you can imagine here, so for example, this driving segment here is nonlinear as is already, right? So it's not like a linear thing that goes upward in slope. It's like a weird box-related thing, but it might fit my data better. Okay. The nice thing about decision trees is that, as you may have noticed, it works with both numeric and categorical data without extra work. So with linear and logistic regression, I have to encode my features in using a one-hot encoding if I want to work with categorical data. With the decision tree, don't have to do that. I can just make a binary rule based on some categorical data. No problem. it's easier to interpret compared to a linear or logistic model. And this is a key trait of decision trees. So it's a lot easier for me to say, okay, here's a set of rules. You should, if it's Sunday or Saturday, you should drive. Otherwise, like check the time of day. Otherwise, check whether you can carpool. And that sort of thing is much easier to communicate to you than saying like, okay, the weight for driving is 0.87. The weight for taking the BART is like, the weight for like Saturday is like 0.2. And you have to like do the linear regression yourself. It fits complex and non-linear decision boundaries without doing feature engineering. So I don't have to do polynomial features in order to model a polynomial. A decision tree can actually do that by itself. And the nice thing about it is that we can use it for both regression and multi-class classification without additional machinery. So you can imagine here, I can have, instead of driving, I can just predict the time it takes to get to San Francisco. And I can have here the decision boundary, or I can have here like a set of rectangles that each one gives me a different time it needed to get to the San Francisco. Okay, so the question here is, how do we actually build a decision tree based on some data? And the idea here is that I have to give you some vocabulary. I'll say that every branch in a decision tree splits the training data into nodes. And a node is pure if all points have the same labels. And so what I do here is, at every rectangular square in my decision tree, we have a set of training points that will fall into that rectangular square, into that rectangle. And a rectangle is pure if all the points in that rectangle have the same label, which means that I have a training set, and the training set says, on this particular day and time, it's better to drive. On this particular day and time, it's better to take the BART. And what will happen is when I cut up that rectangle into smaller rectangles, the points will fall. Some points will fall in different rectangles, and sometimes those rectangles will have points that all have the same label, and that's what we call a pure node. So the basic algorithm here for the decision tree is, I'll start with all my training data in one node, and then I'll repeat the following until all the nodes are pure. I will find the best feature and the best splitting value for that particular node. For example, I might decide that I want to use j equals 2 for hour of day, and I want to say I want to split the data on 10 a.m. And then I'll split my data into two nodes, one where all the data points fall before the split, and one where all the data points fall after the split. Oops. And that's pretty much the entire algorithm. So I just repeat splitting the tree. So I start with all the data in one big tree, and I just split that tree in two over and over again until I can't split anymore. Okay, so the question here is, how do I find the best feature j and the best split value? The intuition here is that good splits find the features that get closer to a partition of my training labels. So let's say I have these three splits. So I might have this node up top, and I want to figure out which split is the best. And so if I look at, so these three are alternative splits, so I can pick one of these splits to use. And the idea here is let's get some intuition about what split would be the best one, or the most informative one. If I split the data in this fashion here, the nodes on the bottom don't really look different from the nodes on the top. Whereas on this tree on the right, if I make this split here, I get a lot of information, right? Because if I manage to make this split here, I can say, okay, everything on the left, I'm going to say drive. Everything on the left, I'm going to say take the BART, and I can stop my tree right there. So the idea here is I'm going to split my tree until all my nodes are pure, and these two nodes are pure, therefore they're better than the ones over here. Not only that, the one in the middle is also okay to do because it gives me some more information about how to split this tree, right? Because if I split this tree in this way, then I can say the node on the right has more BARTs, and the node on the left has more driving than the node at the top. So the idea here is, if I can get closer and closer to a complete split of D and B, then the split is better than the one before. Okay, so this one here is the worst, this one here is good, this one here is ideal. And the basic idea here is I want to find the features that give me as close as I can get to the ideal split. Something that gives me the maximum like differentiating ability between whether I should drive or take the BART. Okay, any questions about this? Okay, to give you one more analogy, let's say I have some points here, and I want to figure out whether I should drive or take the BART to San Francisco. Okay, and it might be the case that I will always drive on the weekday. I will always drive on the weekends, and I'll never drive on the weekdays. If that's the case, then the weekday feature is a great feature to use for my decision tree because it gives me a lot of predictive power as to what I'm going to do. So if I always drive on the weekends and always take the BART on the weekdays, then I can say, okay, I should put in my decision tree, make a decision based on the weekday. And that will perfectly put the driving on this side and put the BARTing on this side. Alternatively, I can have a feature that says, let's say, like whether I charge my laptop today. Okay, if I charge my laptop today, and it might not really affect or it might not provide any indicative power as to whether I'm going to drive or take the BART. So you might expect that if I try to split my data here on whether or not I charged my laptop this morning, I won't really notice any difference in the pattern of driving and BARTing between my two splits. So again, the analogy here is a good feature splits apart my data well, whereas a bad feature doesn't split my data much at all. Okay. And as usual, we'll pick a loss function and minimize that loss function to decide on the best feature. So what we'll do is we'll define an idea called entropy, and then we'll do what we call the entropy loss. If it sounds familiar, it's because we talked about the cross-entropy loss for logistic regression. Those two things are related, but not exactly the same. So the entropy of a node is defined with the following formula, where C is one of the possible labels in my data set, and P sub C is the proportion of points in my node with that class. You can read this as if I pick a random point from a node, and that node has very low entropy, I'll be quite sure of what that point is. But if the node has high entropy, I won't have any clue. Okay, so to give you some intuition here, I'll have you do some practice. Okay, so take that formula, take these three examples, and see if you can find the entropy for each of these three nodes. Okay, so why don't you turn to your neighbor and talk to them about how you approach these. If you're confused, tell them that you're confused and see if you can figure it out together. If you're confused and have a question, see if you can come up with a question to ask me. But do talk it over and see if you can verify that for the first node, entropy is 0. For the second node here, entropy is 1. And for the third node, entropy is log base 2 of k. Okay, so how do I do this? In a pure node, all the points have the same label, have the same class. So let's say that my pure node has 10 points and they're all labeled drive. If I have 10 points and they're all labeled drive, the proportion of driving is 1. So I have 1 here times the log base 2 of 1, which is 0. I don't have any other classes, so I don't have any other terms in the summation of the entropy. Now let's suppose that at the second node, I have 5 points that are labeled drive and 5 points that are labeled BART. The proportion of driving is 1/2, and the proportion of BARTing is also 1/2, because in a node with 5 driving and 5 BARTs, half my points are driving and half my points are taking the BART. So I have here 1/2 times the log base 2 of 1/2, and I have negative that minus that because of the negative sign in front, and I get the entropy of 1. For the last one, if I have k points and k labels, let's say I have 16, or let's say I have 10 points and they're all labeled differently, so they're labeled with different labels. The proportion for every label is 1 over k, or 1 over 10 if I have 10 points. And so I plug in 1 over 10 into this proportion here and this proportion here and take the summation. And since every term is the same, I have k terms. And so I have negative 1 over k times log base 2 of 1 over k times k. The k and the 1 over k here cancel out. And negative log means I can do the reciprocal of the fraction in here to get log base 2 of k. Okay, so how do I read this? I read this as, you can think of the entropy as the loss associated with the node. So if a node is pure, it's good. We should have 0 loss. And the more labels a node has, the more impure it is. And so we should increase our loss if that node is if the node has more labels, or basically if it's impure. So right here I have entropy of 1, and if I have 20 points here, this log base 2 of 20 will be bigger than 1. So I'll have more entropy if I have more labels in my data. Okay. Any questions about this? Okay. So now we can use entropy to decide how good a split is. So again, we have a decision tree, and we have all the nodes in one branch of the tree, or we have all the points in a branch of a tree, and we want to figure out how we should split the nodes up in order to minimize my loss. And we define that by saying, that we minimize the loss if we minimize the entropy after the split. That's the idea for a decision tree. Okay, so whenever we do a split, we'll look at all the possible splits that we can do and pick the split that minimizes my loss. The loss of my split is defined like so. So if my parent node has k points, and the child nodes have k1 and k2 points, we know that k1 plus k2 will be equal to k, because we're going to split my nodes into one partition or the other. And the loss of my split is the weighted average entropy of both of my child nodes. In other words, take the entropy of my first child, take the entropy of my second child, and weight them and take the average. So the reason why I weight these entropies here is that oftentimes we have a lot of points that end up in one node, but not as many points in the other, and we should make sure that the entropy of that node is weighted more heavily than the entropy of the other. Okay. So in other words, whenever we're going to split a tree, we're going to consider all the possible splits, compute this loss in every split, and then pick the split that gives us the least entropy after we split. Okay, so to see if you understand, I want you to have some practice. Here are 3 possible splits. Calculate the loss for each of these splits. Okay. So for the first tree, to calculate the loss of the split, I have to first find the entropy of each of the children. The entropy of the first child, the one on the left here, is 1/3, because 1/3 of the points are labeled D, times the log of 1/3, minus 2/3, because we have 30 points labeled B, times the log of 2/3, and this gives me this particular entropy here. You'll notice that when I do the same entropy calculation on the right-hand child, we get the same entropy, and the reason why we get the same entropy is because the first and the second child have the same ratio of D to B. The loss of the split then is the number of points in the first child times the entropy plus number of points in the right child times its entropy divided by the total number of points, which is 60, but that gives me the same loss as before. So this is 0.918. Yeah, Arun?
So is the split ratio within the child? So for the child, if there was 5 and 10, so 1/3 and 2/3 is the ratio within the 15.
Yes, that's right. So the ratios here are the ratios within a child, not the ratios of the parent or the other child. So every single entropy calculation here is for one box. Okay, so that's the loss for the first split. Here's the second. So this node here has an equal number of D's and B's, and we've gone over how the entropy of that is 1, but you can also do that calculation yourself. It'll be like -1/2 times log of 1/2 minus -1/2 minus 1/2 of log of 1/2, which comes out to 1. The second child here, likewise, is 1/4 times log of 1/4 minus 3/4 times log of 3/4. That comes out to be 0.811. And the loss is the weighted average, which comes out to be 0.874. Okay? Now, the easiest one is the last one, because the entropy of the first child is 0. It's a pure node. Entropy of the second child is also 0. It's also pure. And so the overall loss is 0, because the average of 2 zeros is a 0. Okay, so here we go. The information gained by a split is defined as the entropy of the parent minus the loss of the children. So in other words, the loss for the first split here is 0.918, and since the parent node also has the same ratios of D's to B's, it has the same entropy as each of its children, and the information gained is 0. Okay, so we have the loss of the second split and the information gain, and we have here the loss of the rightmost split and the information gain for the rightmost split. So you should easily be able to find the loss of a split as well as the information gained by a split. Okay, so I want to give you a gut check. The gut check is, okay, well, if the rightmost split is always good, why can't we just pick it every time? The reason why we can't pick it every time is because there's not always a feature that perfectly splits apart my labels. Right, so I said before that if it just so happens that I always drive on the weekends and never drive on the weekdays, then I can pick this rightmost split, but there's no guarantee that there's such a feature. So it might not be the case that I always drive on the weekends. Maybe sometimes I take the BART as well, and in that case, using that feature will not perfectly split apart my data. Okay, I have here a demo. Sadly, I'm going to cheat and just show you the code. I have here some code to compute the entropy and the loss of a split. You should be able to look through this and define it yourself. It's a translation of the math into Python, so it's hopefully straightforward. And what I've done here is I've taken all possible 2-class nodes. So I've taken all nodes where each node only has 2 labels, 2 possible labels instead of 3 labels or 100 labels. So I just have here 2 labels. And we notice that the entropy formula gives us the entropy for every proportion within these nodes. Okay, so this node on the leftmost has none of class 0, whereas this node on the rightmost has all of class 1. Sorry, not all of class 1, all of class 0. So this is like all zeros, this is no zeros, and this is all zeros. Getting a little mixed up here. And we see here that the entropy of a pure node is 0. The entropy of a pure node is also 0. And in between, the entropy increases. We also saw before that if you have a node that's 50-50, like one class and the other class, we have an entropy of 1. And we see that again in this graph here. So we have here 0 entropy, 1 entropy, and everything in between. Okay. Now, I have here a graph that shows, okay, so whenever we have a node has a particular entropy, and I plotted the parent entropy and the blue point. So this is a node that we're going to split. A split of a node ends up with 2 children, and each of those children also have an entropy. And I plotted each of those entropies via the orange points. It turns out that if you draw a dotted line from the one orange point to the other and calculate the split entropy, the average weighted entropy of each of the 2 orange points, the information gain is this green line here. Which means that if you can find 2 children, what you want to do is you want to try out all the splits and find which combination of orange points gives you the tallest green line. And that's another way of visualizing how you pick the best split for a decision tree. Okay, so here we go. We notice here that the information gained by split is always positive, except in 2 cases. One case where the split puts all the points in one child node, and the other case is where the child nodes have the same ratio of labels as the parent node. For those cases, the information gain is 0, and you can verify that that's the case. This is true for strictly concave loss functions, and by concave, I mean that if I draw a line between 2 points on the curve will always be above the line. It will never be on the line or below the line. Okay, so see, I have just enough time for my last demo, but here are some questions that you should ask your TA and try to understand yourself. Is why won't we ever gain entropy by splitting my data? What is this dotted line and what does it represent? And are there possibly non-strictly concave loss functions? Okay, so again, how do I fit a decision tree? I put all my training data in one group, and then I repeatedly split the group. How do I split the group? I find a grouping that's impure, and find the best split for that grouping, and then I split that group until I get all my groups are pure. And that's about it. Okay, so let me show you really quick here how this works. So I have here the cancer data set from before. I have here some rows, and I want to predict whether this particular cell scan is malignant or not. Okay, so here I'm going to make a prediction based on mean texture and mean radius. Okay, so I have here some functions that draw for me the decision boundary of a classifier. And what I can do first is fit a logistic regression classifier, like so. And I can pass in, let's do solver equals saga. I can fit this guy on my X train and my Y train. There it is. It didn't converge, but I'm going to ignore that for now. And I'm going to draw the decision boundary. Let's do that. There we go. So here is the logistic regression decision boundary. It's linear because logistic regression gives linear decision boundaries. And I can show you now how a decision tree does its job. So here I have a decision tree. I'm going to limit the depth to 1, which means I'm only going to do one split. And if I only do one split, I either get one vertical line or one horizontal line. But in this case, the best split was a vertical line based on the mean radius. So this decision tree says, if a point comes to me and its mean radius is less than 15, I'm going to say it's blue. Otherwise, I'm going to say it's orange. I can increase this depth. So if I go from depth 2, I have one more split. See if that runs. It's a little hard to see, But I think there are like 2 vertical lines here. So if I go to depth 3, I think it's easier to see. So I'm just making my tree grow deeper and deeper. So we can see here with depth 3, I get this kind of staircase decision boundary. And I'm now going to let it go to maximum depth and just let it run all the way down until all the nodes are pure. What do you notice? You notice a very wacky decision boundary. And the reason why it's very wacky is because it's trying to make every node pure. What that means is this orange point right here, it will have to, it like says I must label this point orange at all costs. And so I'm going to make sure I get the rules that will make this area here orange, but that gives us this little weird orange strip over here. Similarly, this blue chunk here, it says I must label these points blue, so I'm going to put a blue chunk right here and make the rules in order to make that region blue. Okay, so what we notice here is some problems with the decision tree. First of all, a decision tree, when you grow it out all the way, will always have 100% training accuracy, but it also means that we'll always overfit the data, almost always. There are many ways of approaching this overfitting, but there is a very clever way of approaching the overfitting via bootstrapping, and we'll save that for tomorrow. Thanks, and I'll see you tomorrow.